doing, but with the microphone switched off, so I was not successful.
Okay, so we have now about half an hour to discuss various issues, and in fact, the organizers have prepared during, I don't know when, at some point while sleeping, they must have prepared this nice summary of yesterday's discussion. And so some of these topics could return, of course, again, if somebody wants to continue now, perhaps in connection in particular to asymptotic safety, or I can imagine that several people in the audience have open questions about asymptotic safety, what it means, and so they have a chance here to clarify those points.
Okay, have a good luck as chairman.
Sorry?
Have a good luck as chairman.
Oh, well, nobody's asking questions, so.
Yeah, this is a good part.
There is Gia. There is Gia who will ask a question.
Oh, Gia has appeared. Yes, very good. So, Gia,
no,
please.
Gia has to be careful. If he starts to ask questions, it can be very dangerous.
I can mute him. I have the power to mute him.
Yeah,
okay,
so
okay.
you can,
Then
you
it's
can
fine.
use your power. Yeah, I was trying to somehow formulate the question. So probably to all the speakers of this session. So I still don't understand how is the problem with ghost cured in this approach. Yeah, I just don't see any way out, any clear way out that was presented. Is this and my problem is a really textbook problem, because I mean we know that the correlator T-mu correlator has a unique spectral representation, and if I normalize this correlator to Einsteinian gravity in deep infrared, the spectral function can only be positive. If it's negative somewhere, then I have a ghost pole or a branch cut. Now, so how is this problem cured? This is what I'm trying to understand in this approach. Is this an assumption, or is some of the properties sacrificed, yeah? So but probably I'm sure it's my problem. Probably I'm missing something, but I'm really confused about that.
May I comment on this?
Okay.
Yeah, sure. I mean, whoever has.
Okay, Gia, I think the problem of ghosts cannot be cured in this framework, and the reason is the following: you can modify perturbation theory, or do something else with poles, with regularizations, with weak rotation, and so on. And then you get formally, you can start with another theory when you have in the Lee-weak scheme, you have unitary theory at the tree level, no problem. Put more derivatives like we did with Modesto, 6 derivatives, and you have unitary theory. But the problem is that I think the main difficulty is the following: the S matrix approach in gravity is not reliable, because it's not particle physics. In particle physics, S matrix means that you are working with a scattering problem. So in the initial state, you have free particles, and the final state, out state, you have free particles. In gravity, if you have ghosts, they are massive, so they interact with gravitons automatically, S matrix by construction. So the main question is stability, not the unitarity, because unitarity is unclear what it means. I have other arguments, but I will just keep it. And with the stability, it is classical stability, as Stravinsky said yesterday, by the way. And Strumian in his
I just want to follow step by step, because you are going too fast. I mean, first question was whether there is a ghost. This is the question, and you are saying there is a ghost in this theory.
No, if you
Then we
put
can,
the ghost,
then we can
there is
discuss
no-
later
if you
how
don't
to
put
deal
the
with
ghost,
it.
there is no ghost. Because
So
the last
maybe-
two talks were about completely different subjects.
No, my question is based on a textbook. I'm not inventing anything. I'm just saying, we know that the correlator has, if we assume standard analyticity properties of the quantum field theory, regardless of the S matrix. I mean, by the way, string theory is formulated like as an S matrix theory. So I disagree with the statement that in gravity S matrix cannot be formulated. That's absolutely not true. But I don't want to enter there. I'm just saying, let me assume standard textbook analyticity properties. Then with this assumption, I know that the correlator has a unique spectral representation. Now, if I normalize, therefore, this correlator to Einsteinian gravity at some point in infrared, I cannot make it weaker without making spectral function somewhere negative. And that means that this theory would propagate a ghost. Now, the question is,
even in Einstein gravity.
No, in Einstein gravity, there is no ghost. There is no problem. In Einstein gravity,
Sure.
correlator
Okay,
is normal.
Maybe can I say something? Okay.
Yeah, Ilya, let's see first if some of the speakers want to reply to Gia, and then.
Yes, so I can say something, and maybe if my answer is not complete, Franco or Astrid can add something else. What is the point? So it is clear that if you truncate the axon and take r plus c squared, you would see a ghost, but it is not obvious that the ghost is in the theory, because if you sum all of the terms at the level of the effective axon, the effective axon
my
could
question
be...
is not about truncation. My question is even more basic. I'm just saying the correlator has a unique spectral representation. I don't need to know your theory. You have some theory, let's say, right?
Yes.
You tell me, okay, here is my theory. And I can make a test. I can tell you, okay, compute this correlator. Give me the spectral representation of this correlator. I don't need to know anything else. And from there, I see that I cannot make gravity weak in UV unless the spectral function is somewhere negative. This is my problem.
No, it is not obvious, because in the UV you can have something local that makes the theory UV complete, but still at the level of the effective axon could be non-local and remove the ghost. And talking about practical computation,
this is precisely my problem, because then you see, I hear this, I understand, I hear these words, non-locality and stuff, but I want to reconcile with a really basic knowledge of quantum field theory. And so think in the following way, right? I mean, in Einstein gravity, you have a single pole. That's a single massless pole. All right. Okay. Now, the moment you modify gravity in some way, you acquire new poles. Now, the question is whether these new poles, they add with the same sign. That if they add with the same sign, then the spectral function is positive. Then everything is fine. If some of the poles add with opposite sign, then the spectral function somewhere is negative. Now, to make gravity weak, you need to add some of the poles with opposite sign, because you need to somehow cancel the effect of Einstein graviton. And that's the basic problem. And this question is completely independent of the theory. So I don't need to know from where your theory comes. This is like if the correlator.
What you are saying is absolutely correct, 100%.
Okay, so
actually,
then
I wrote it in many papers.
Okay, how do you cure this problem then?
There is no way to solve this problem.
The spectral, some people computed the spectral function at least within some approximation, and it turns out that at least the one related to the fluctuation, it is positive. So
how can it be? Look, I mean, you cannot add two positive numbers and get a smaller number. That's impossible. So spectral function has to be negative somewhere in order to make effect of the gravity weaker than you have in Einstein. I just don't see how you can make it weaker otherwise. If its spectral function is positive, then you're always adding, and new contributions are adding to Einsteinian graviton, and then you are increasing strength of gravity. That's okay. In that case, it's okay. But
only if you have two terms. I mean, if you have the Einstein-Hilbert term plus, say, C square, you only have two contributions, right? And then you get opposite signs. But
yeah, for example, that's an example when you opposite
yes,
signs.
but in that case, it is a too simplified case because you only have two terms, so it is clear that one of them.
No, if you can infinite number of terms. What I'm saying is a triviality. I'm saying that spectral representation has to have somewhere a negative contribution. Otherwise, you are always increasing the strength, because if everybody comes with the same strength, think about exchanges, okay? Think about two energy momentum tensors, and you are exchanging. In normal Einstein, we exchange one graviton. And now, in order to change the strength of gravity, I have to exchange new particles, new continuum or discretum. That's a separate story. I need to exchange new stuff. And if all the stuff adds to it, then of course I will make strength, I will strengthen gravity. So some of the exchanges should contribute with opposite sign. I'm saying a total triviality.
If I may say something.
Let's hear what Anupam has to say quickly, please.
Yeah, so Gia is a good point, but also what happens exactly as you said, that terms are infinite. They're not, it's not finite. Yeah. It's infinite, and they come with exactly what you said, plus, minus, plus, minus, plus, minus. But if you sum
minus is not is not good, Anupam. That's what I'm trying to say.
No, but it's exactly the entire function. You get there is a theorem which you can establish. And this is exactly what appears in string theory, by the way. That in the string theory, why it makes it UV finite. If you look at the green function of the string, the famous paper by Gross and Mende, look into the 2-point insertion, you will find precisely what you're saying, that the way this string theory makes it finite.
String theory is propagating infinite number of high spin fields. That's a different story.
No. I mean, yeah, it has infinite power. We all agree.
I'm talking about T mu correlator in quantum field theory.
Yeah,
that's all I'm talking about. Yeah. What I see from analyticity properties, the spectral function has to be positive everywhere.
Correct.
Now, if it's positive everywhere, then you will make gravity only stronger. How can you make it weaker?
Well, there are certain choice of form factor which you can make it negative.
It's probably me. I'm not saying, probably I'm the one that is confusing something, but I don't see the answer to this. I mean,
okay. Maybe Daniel has an answer.
I'm not sure whether I have an answer, but I'm not sure to what extent we really can believe that spectral functions physical spectral functions must necessarily be positive. I mean, I think a good example could be by looking into QCD, which has been cited as an example a number of times. And if you were to be looking into how the spectral function for QCD looks like non-perturbatively, what people are finding is that non-perturbative spectral function can become negative.
No, of course, but QCD is not a good example because
this is not an argument against.
No, I fully agree with you. I fully agree with you, but that's specifically, my question is specifically about T mu correlator. This is very important.
Now we're talking about gravity, and gravity, I mean, the proposals on the table that gravity may become in some form non-perturbative. Okay, so one would have to understand ways on how to accurately compute the spectral function now for a graviton propagator. And the only point I wanted to make is that a priori, I do not, as of yet, see a very convincing argument that such a spectral function necessarily must be positive everywhere. Okay, I do see QCD as an example. Okay,
that's not a good example.
It is a good example because the theory.
No, because in QCD you have different colors. That's why in QCD, also in electrodynamics, you can have positive charges, negative charges. You can have colors which have different. You can have anti-colors. I was asking specifically a question about T mu correlator between two energy momentum tensors. That can only propagate spin 2 or spin 0. If you do, I mean, from just completeness and group theory, we know that all the poles that can be there should be spin 2 or spin 0. For those, as I said, I mean, And my question, I don't see connection with whether you are computing it perturbatively or non-perturbatively, because even if contribution, I'm not asking how you compute it. I'm just saying you give me the full spectral function, and it looks like, at least naively, for a naive listener like me, I'm not in the field, in that field. Naively, it looks like that there is no way not to make it negative somewhere. So my question basically is, if this problem appreciated? Is it somehow cured, or maybe it's also okay? Sometimes we have a problem, we don't know how to solve it, but we assume that it's somehow solved. We postpone the solution. That's also
so
okay.
Perturbativity is cured. What you are saying, perturbativity is cured. And actually, I have cured it. That's what I'm saying.
So how?
What happens?
John had raised a hand earlier on.
Right, so I think now? Daniel's point is technically correct in that anything that's coupled to gauge currents, actually the positivity rules don't strictly apply.
Yeah, I agree with
I don't think it's really the answer, because for example, in the QCD, the violation of the positivity is just logarithmic, and we really need something much more strong here. I suspect that there is some change in the analyticity structure that's generally assumed in the Shalen-Lemon representation. And I think you can see that in Frank's example, where Frank had this infinite series of poles running up on the imaginary axis. That changes the analyticity structure, because those poles sit as you're trying to rotate to Euclidean. And my suspicion from other calculations is that Frank probably would have some issues with causality on small scales, just like I claimed. And that's where we've given up one of the axioms of that spectral representation. And if you do that, you can write a different spectral representation with these conjugated poles and a standard spectral function that does have the suppressed high momentum behavior compared to the usual representation.
No,
so
thank
we
you.
we have given up one thing
that fully resonates with
thing, which is the analyticity structure.
That fully resonates with my expectations. Let's say, I think it makes perfect sense what you are saying. Probably that's the answer. Probably there should be some of the analyticity properties should be given up.
Should be given.
Yeah. Frank,
I have doubts that you actually violate causality with these particular set of poles. So I think you can naively compute what the causality violation should be at the scale, and it's 0. Yeah. So this is something that I would like to discuss with you. But my expectation is with this particular example, you save microcausality. It's precisely tuned for that.
0 on scales larger than the scale of non-locality. Frank?
Yeah.
You mean that it becomes 0, that it of course, it drops exponentially once you go outside the region of non-locality.
Yeah, okay.
I think I would agree with John what John is saying, because I mean, usually in quantum field theory there is no free lunch to we have to sacrifice some of the properties to get. So I would think that you have to sacrifice analyticity properties. Now, normally I would immediately agree with John that the moment you sacrifice analyticity properties, that will come back as some sort of violation of causality. But I don't know. I didn't do this analysis. So you are saying you can give up certain analyticity properties, but still maintaining causality.
That would be my expectation, yes.
Right. If I may say, no, you will still violate causality. you will still violate causality and locality in the region of non-local. Suppose this is a non-local region. Here you are violating everything, but not on scales outside this.
Sravan had question.
Hi. I would like to continue the question I had asked during the Frank's talks, and it's also related to the question he has raised. I mean, to have ghost free, I mean, to not have ghosts, the form factors should take a very specific form in the non-local theories, as it was shown by Krasnikov, who is here with us. Well, the point is about the predictivity. I have a question. So, I mean, you say that you can predict the form factor using solving Wetterich equation and assuming some fixed point exists in the UV, one fixed point, that one fixed point. Am I correct?
Certainly, there's more than one fixed point.
Okay.
And I'm not assuming it. I would show that there is one. It comes out of the computation. So what you're really solving is the Wetterich equation becomes a coupled set of nonlinear partial differential equations, and you look for solutions of this equation.
And you do not
satisfy a set of criteria, then you would say this is a fixed point.
And the form factor you have fixed, is it ghost free already? I mean, if the Wetterich equation is powerful to give a form factor compatible with ghost freeness?
I would say
in the UV, at least around
there is some evidence, yes.
Okay. And another parallel question, because you have a toy example with some form factor like tan hyperbolic box, where you have asymptotic safety because the form factor goes to constant at very high momenta. Okay,
yes.
I mean, this is a toy example. Does that mean like you still have a large degrees of freedom? I mean, large degree of choice for the form factors. It's impossible to fix or make at least few or finite number of form factors. Is it not enough the approach? I mean, just I want to hear your comment about this.
There will certainly be freedom in choosing the form factors. But what we want to achieve with this toy model is we want to identify the structures that you want to track when solving this differential equation. But this is the next step in order to construct really solutions of Wetterich's equation, which are capable of tracking a pole structure in the complex plane.
Okay.
And then in the end, if you do this exercise of solving the equation, you want to show that they are precisely aligning in such a way that it is ghost-free.
And the question, like in the Wetterich equation, you have the scale K, it's RG flow scale, right? I mean, it cannot be related to the actual energy scale we normally think of. I don't know how to derive.
In the form factor program, you shouldn't.
Yeah, in the form factor program. So then how to understand really from physics from IR to UV? I mean, not just around the physics around the fixed point, but between the fixed point. Let's say, I mean, there is IR fixed point and UV fixed point, and can we understand? Can this equation will give enough sufficient understanding of the whole theory at all? I mean, energy scales.
Okay. Let me give a provocative answer to this. Say you make a computation in standard quantum field theory using a Feynman diagram with a loop. And you stop integrating out the loop momentum at some infrared scale lambda. What would be the significance of your result? Would you attach some physical meaning to it?
But here you integrate out some IR scale, right? I mean, well, usually I integrate out at I put a cutoff scale and integrate out all the heavy modes above the cutoff scale. then it
if
will
you
be
do
some
a
effective
Feynman
field theory.
diagram, you would always compute over all loop momenta.
Yes.
And if you say, I want to give a meaning to the Wetterich equation at finite values of k, you would give up this principle. Then you are only doing part of the diagram, and k gives you the scale at which you have stopped integrating out the loop momentum. There might be some physical situation, in particular in condensed matter, where it makes sense to give an interpretation to such a computation. But in general, in quantum field theory, I doubt that you can do this.
Well, there could be some situation in which there is an actual infrared cutoff, and then
yes, if you have a mass, then you are fine.
Sure.
But if you are massless, then you should integrate down all the way to k equals 0, and then you extract the physics.
Okay.
And another short question. I mean, in the yesterday we had discussed extensively about that these additional term, logarithmic non-local terms, which comes from on-loop quantum corrections. So, in your approach, the form factors are analytic or non-analytic. You make an assumption about it, or I just want to understand, because in the local theory, when you compute loop corrections, you have these non-analytic form factors like logarithm of box. And do you get such terms in your calculations?
There is some evidence that there are relations between different form factors, and the fixed point controls these relations. But I would say it's not completely understood yet what the freedom associated with these form factors actually is.
Okay. Okay.
Luca, you had a question?
Yeah, just maybe related to this last point on form factors to Frank. So yeah, what Frank showed is basically on some toy model, let's say some proof of principle of form factor in Minkowski, okay? But in general, we don't even know if, for instance, one form factor which is ghost-free Minkowski will be ghost-free also around the other backgrounds, okay? And I think there will be also a talk about this on Thursday in the second session. So what is not clear for me, so you would expect like that from this Wetterich equation, would you get some kind of ghost-free form factor which is background independent and give you like some kind of ghost-free condition around any background? Or because it seems that all the treatment you were doing was in Minkowski, right? At least the analysis that you did of one factor. And it's very trivial that if you go to the sitter, you
highly non-trivial.
can violate ghost-free condition. Yeah. So, I mean, your expectation is that from this Wetterich equation, you should get some kind of effective action, which is ghost-free around any background. I mean, any kind of background, or is limited to Minkowski?
No, in principle, you could do any type of background. It just becomes exponentially harder, and already the Minkowski space computation is hard.
No, yeah, but in the end, you would expect like one effective action, which is, I mean, the same for everyone. Okay, well, this is really not trivial.
Yeah, definitely.
Because I mean, the form factor, yeah, we will hear this, I mean, on Thursday for sure, but may depend also, I mean, not just on box, it could depend also on curvature itself. Like, so.
If I may say,
perhaps I can just comment that I mean, Wetterich equation is not something particularly magic or exotic. If you do one loop calculations with the Wetterich equation, well, I mean, that equation is just a tool to compute the effective action. And if you do one loop approximation and you work in an effective field theory with the Wetterich equation, you will compute the same effective action that you would find by any other means. You would find a log box and so on. It's just, so now the idea is that, however, we would like to impose some initial conditions on the evolution of the RG, starting from some UV fixed point. So that is what puts some restrictions on the trajectory. And that is what then allows you to make predictions for the effective action at low energy. That could go beyond the predictions of the effective field theory.
Okay, I see. Can I just make a small comment?
Sure.
Small comment. Yeah, just related to the first question by Gia. So yeah, basically, I think we will see one more explicit example of this, basically like a correlator which can be more suppressed but still positive in the next talk. In the first session, I mean the second session, the first talk of the second session of today. And basically, as also John was saying, you should change anyway some kind of property in your complex plane. For instance, you can have some kind of exponentially suppressed propagators, okay, which like, I don't know, some kind of e to the power some polynomial, okay. And these exponential propagators, of course, they are changing the analysis in the complex plane because they're introducing some kind of, no, they're introducing essential singularity at infinity. Okay, so you are paying a price anyway. But if you can modify your prescription to analytically continue from Euclidean to Minkowski, you can still define something which makes sense. And it seems to be, indeed, that's the case in string field theory, where you have this kind of exponential of box which appear in the vertex, okay? And so they change really the analyticity property, okay?
Yeah, but I think it's sort of a little bit consensus is that one has to change analyticity properties. That's the price.
Sure, yes,
that's
sure,
the price
yeah.
to pay. So
sure.
And then of course it's case by case basis whether the theory makes any sense or
totally, yes,
yeah.
Of course, yes.
But this is also happens in string theory also. So in some they also do the same business.
In which sense? So.
If you look into the green function in the worldsheet, at the level of worldsheet, if you look into the green function of say 2-point insertion, you see exactly the propagator will be like some kind of like exponential of an entire function or something like that. And that's one of the reasons.
In string theory, I don't think you violate analyticity properties. I think in string theory propagators, their analyticity properties are pretty standard.
Pretty standard, but exactly the point which you said, that since we are summing over all possible, spin states, when you sum them, then exactly
that's yeah. So sure. In other words, I was saying, you see, the way I was okay. I think it's all answered, but I don't want to take any more time. But here, if the approach is that we don't want to introduce additional spin states, and let's see if quantum field theory itself can do the job. That my question was applying to that part. So then I know what I have. I have spin 2 and spin 0 as an exchange and stuff like this. Can I ask another question? I don't want to dominate the discussion, but and a little bit unrelated question.
Okay, go ahead.
Is that okay? I'm not jumping in.
Maybe we should allow first Anish to ask his question, yes, because he raised the hand.
So sorry, I just had a small curiosity for Astrid's talk. So maybe I've just missed it. So when you have this asymptotic safety in the gravity sector, and let's say in the matter sector I have a U1 theory. I have a gauge U1 theory. So my gauge U1 theory suffers from the Landau pole problem. So is it possible to modify the gravity sector in such a manner that my Landau pole problem for my U1, I mean, just U1 can also be cured, or I mean, my matter sector, this problem will still remain no matter how much I modify the gravity sector?
Yeah, so this was one of the things I didn't talk about, but there's quite a bit of literature looking into that from the perspective of asymptotic safety, finding a gravitational impact on the U1 coupling in such a way that could become asymptotically safe or asymptotically free, as long as the infrared value of the gauge coupling is below an upper bound. So if the infrared value of the gauge coupling would be too large, then you would still run into the usual Landau pole problem. But if the infrared value of the gauge coupling is low enough, then the effect of asymptotic safety could be sort of strong enough to get you into asymptotic safety or asymptotic freedom. And again, the usual caveats are attached that this is, a study in Euclidean signature within truncations of the functional renormalization group flow, but the qualitative effect is actually quite stable under various truncations that have been tested. again, if you come to exact, quantitative numbers, then that's a different story of sort of, getting convergence in those. But the qualitative effect, I would say, is robustly present in all of the studies to date.
So this limit or the value that you are saying for in the infrared U1 charge. So for the standard model, does it satisfy, or are you talking about like a dark U1 sector? You can do it in a U1 extended model.
Yes, so I mean, if you just apply sort of the state-of-the-art truncations and look at the numbers, then the conclusion would be that the upper bound should be above the actual U1 standard model value. But I mean, as I said, those numbers, you should view them attached with a significant systematic uncertainty.
I see. No, I remember very long ago that there was a paper by Frank Wilczek who started this standard model U1, and he was not able to solve, or rather he made some specific comments in his paper saying that no matter how much I modify the gravity sector, it does not affect the Landau pole, particularly the Landau pole problem in that context. So therefore, I was a little curious. Or maybe you need different kinds of methods, like a heat kernel method, where you don't care about the Minkowski metrics.
Let me make a comment on that sort of that. There's a whole branch of papers that follow from the Wilczek-Robinson paper. And they specifically only ever look at the beta function in the matter sector and the gravitational contribution to that. And now, beta function in general is not a universal quantity. And so there will be a scheme dependence in those beta functions and in the effects. So the thing to actually look at to understand whether or not there is such a gravitational impact is the critical exponent that you would get associated to the gauge coupling in the UV. And that there are indications that actually remains stable under changes in the scheme. Whereas if you just look at the beta function for the matter sector and then change your schemes, you could draw various conclusions from that because you're not looking at a universal quantity. So this is important to keep in mind in that context, that you have to carefully isolate what would actually be a universal quantity to look at, from which you could make this judgment whether or not there is asymptotic safety or not.
Thank you.
Okay, so Gia, you wanted to ask something else?
Yes, I have another, sorry, I have another confusion, sort of. And that has to do with black holes and this approach. Because let me do the following thought experiment. Let's say I take E plus E minus and accelerate and boost them relative to each other with a center of mass energy, which is like solar mass, okay? And now, if I'm someone working in semi-classical GR, I don't need much knowledge. I only need to know that black holes are there, exist in a theory. Then immediately I would predict that if there is a head-on collision, the E plus E minus will form a solar mass black hole. But in your approach, you are saying that E plus E minus at solar mass center of energy can have a perfectly nice scattering, like E plus E minus into E plus E minus. And I don't see how these two are reconciled. In other words, I would think that in your approach, if your approach to quantum gravity goes through, you should abolish black holes, because then black holes become sort of both redundant and also they somehow a little bit they contradict the picture, because yeah, that's my question. I mean, what would be the way out from this sort of a paradox?
Maybe I can react to that.
Yeah, if you wish. Yeah.
Yes. So I mean, the first point would be that, of course, I mean, your analysis is based really on the assumption that at high momenta you still have just the standard gravitational dynamics.
No, that's not an assumption. Because the only thing I need to know is that black holes exist of solar mass. Because once the energy enters the Schwarzschild sphere, you form a black hole. There's no question. In semi-classical gravity, if it's Einstein's semi-classical gravity, you do form a black hole.
But I think we have to be really careful, right? I mean, so the black hole forms under certain conditions in semi-classical gravity, where you have, like, for instance, a collapsing shell of dust, and so that
head-on collision, two E plus E minus head-on collision. The black holes form in semi-classical gravity.
From the question of having really particle scattering, where you're in a deep quantum regime. For the matter, and also one thing that I would like to highlight that I think is maybe a general confusion about asymptotic safety is this question of whether this really needs to be something that holds all the way to the very far UV, or whether at some very Transplanckian scale you could have some other theory that matches onto that.
So your question. So just to understand, you are questioning whether black holes will be produced. That was precisely my point.
Whether there is a certain dynamical regime in which black holes really will be produced. I'm not.
So then you agree with me that you have to change.
Deep classical regime, you will definitely produce black holes under the certain, under the.
No, I'm giving a very concrete regime. I can give you an arbitrarily high center of mass energy, galactic mass. Okay, I can give you E plus E minus of galactic mass, head-on collision. Now in semi-classical gravity. There is a consensus that you're going to form a black hole. So now, then in your theory, you should say that that's wrong. That this is not the case, and instead, E plus E minus will approach each other and rescatter like normal particles.
Yeah, I think that's what we are saying.
That's what you're saying.
That there are.
I don't see how that can happen. Sorry.
Under which you will not produce a black hole in certain setups, and that you need to carefully investigate which initial conditions within a given effective action do actually just lead to standard black hole production, and there will definitely be a classical regime where that will happen.
No, sure,
and then a regime.
No, it's not classical regime. Yeah, no, it's not. Sorry, it's not. Sorry, let's clarify the point, because otherwise we will not understand each other. I'm not talking about classical regime. There is a full consensus in effective field theory of gravity. I don't think there is any doubt that any source of energy, once it's localized beyond the Schwarzschild radius, forms a black hole. So this energy doesn't have to come from classical source. This can come from E plus E minus. E plus E minus are perfectly initially quantum states, and this forms a black hole. I am as careful as I can be. So it's not, you cannot tell me that I'm not careful. So now the point is that you are saying that in your theory this should not be true. Now, I don't see how this can happen if your theory flows to Einstein gravity in deep infrared. I just simply don't see how can you avoid formation of a black hole.
No, but I mean, I would say that, I mean, in general, the effective action in the setting would not reduce to just Einstein gravity ever. There would always be additional higher order terms, and there is a dynamical regime in which these higher order terms are negligible. But there is also a dynamical regime in which these higher order terms are not negligible. Right, the regime which you would call sort of the UV regime, or the regime where you start the asymptotic safety. And for that to happen, you need to have higher order terms present in the effective action. And so depending on which setup you're looking at, these terms will or will not play a role for a question like, do you form black holes? So within that larger effective action that does have additional terms, it does reduce to Einstein gravity in certain settings where you can neglect the higher order terms, and then the classical black hole formation story definitely holds. But then there are settings where you have to understand whether the higher order terms that are present, what they do to the dynamics, and whether you do form black holes in that setting. And I mean, just purely at a classical level, if you go beyond Einstein gravity, then the formation and stability and so on of black holes in modified gravity theories just isn't understood very well yet. And so I think the honest answer is that we don't know what the prediction of asymptotic safety for black hole formation is. But I don't think that it's established that just because some regime of the theory has to reduce to Einstein gravity, that says that all of these experimental setups necessarily have to lead to black hole production.
Very good.
So if I understood correctly.
Yeah, I think you understood.
If I understood correctly, so you are saying that the theory doesn't reduce to Einstein gravity in infrared. That's what the claim is.
I would expect that it reduces to Einstein gravity.
There's going to be there's going to be a whole day on black holes, and so perhaps we can postpone discussion of black holes in asymptotic safety to that session. We are running a little late, and there's just one more question by Anna Tokareva, who's been waiting for a long time. Anna, yeah.
Yeah, hello. I have kind of a comment regarding the asymptotic safety program. There is a fun coincidence in the standard model. If you run a beta function of Higgs to Planck scale, then it happens just numerically that within some choice of top quark mass, which is still allowed by experimental data, you can get such a thing that exactly around the Planck mass, the beta function of Higgs is 0, and at the same point of energy, the lambda of Higgs is also 0. So you have kind of decoupling of Higgs, vanishing self-interaction of Higgs, exactly at the Planck scale. Can this fact be somehow implemented into the paradigm of asymptotic safety?
Mm-hmm. Yes, so there's actually work by Misha Shaposhnikov and Christoph Etterich from 2009 who looked at exactly that question, whether this sort of initial condition that you're mentioning at the Planck scale, whether that could come out of asymptotic safety. I would say the answer is not fully settled as to whether the exact numerics of that work out, but the sort of qualitative idea that gravity fluctuations would drive the quarter coupling towards 0, that is something that is observed quite robustly. So whether you indeed then get exactly a Higgs mass of 126 GeV or not, I would say that that is not a settled question. So then the exact numerics again come with systematic uncertainties. But the qualitative effect that quantum gravity fluctuations drive the quarter coupling towards 0, that is observed quite robustly. And so in that sense, that would align nicely with exactly that observation that you were just mentioning.
Fedor has a question.
Yeah, it's a bit of a follow-up question to Anya's, because I remember that nicely, that work by Misha and Christoph. As far as I remember, the story was, so apart from precise numerics plus minus 1 GeV, which is okay, complicated QCD stuff, there was, at least at that point, some, so the idea was that after the M-Planck scale, the running of the all coupling constant change. But at that moment, there were several different calculations of the coefficients for the modified beta functions for different couplings for gauge and fermions. And okay, for some choices of the signs, yes, one could arrange cancellations and arriving to the asymptotically free state. But there were some, at least at that time, there were some calculations of the changes of the sign of the beta functions that basically had opposite sign, and they were not leading to any asymptotically safe regime at all. Just interested, do you know whether this was settled somehow or not? Because at that moment there was basically half of the theoretical predictions allowed for this numerical magic to happen. Half now.
Yeah, no, I mean, so since 2009, since that paper, quite a bit of work has happened on that. And so in particular, this coefficient of gravity in the scalar sector has been computed in a number of truncations and found to be sort of robustly the one that would be needed for this scenario to pan out. The reason why I was being careful about sort of, saying things about the numerics just now is sort of this whole more complicated story that I sort of very briefly touched upon in my talk, that the remainder of the standard model and the actual structure of what happens with all of the Yukawa couplings in the full gauge Yukawa theory with mixing, all of these questions are questions where in Misha's and Christoph's paper you just have to put in a bunch of assumptions, and where we're now sort of working out the details much more carefully to see whether indeed a prediction like that would pan out numerically or not. If you want the evidence that the qualitative structures for such a prediction are there, that has definitely strengthened since 2009. But then one needs to really more carefully look at the full standard model and all of these details to make this into something where you can say it's now really a testable prediction.
Thank you.
So I would like to go now towards the conclusion. There's a couple of raised hands still. So yes, Stravan.
I mean, I want to read one question which we had discussed yesterday, and also I think it's relevant for today's as well. I mean, so in all the discussion yesterday and today, we have been viewing gravity from the point of view of QCD, right? Okay, well, we have QCD, this is what happens, gravity, this could happen, you know, separating quantum and classical. So QCD has been, we have been discussing about QCD. Well, the question is, I mean, is it really needed for quantum gravity QCD analogy? Okay, if not, I mean, my question is related to observations. Do we have any observational indications? If not, can we have observational indications by any means? I mean, that is the most important thing, right? To test any approach. So, I mean, many things we discussed in the last 2 days.
But that's the problem with all of quantum gravity, right?
Yeah, that's true. I mean, just maybe there is some thought experiments. I mean, do we have? I would like to hear if anyone have any thought experiment to, if we can test some way, either cosmological or astrophysical observations.
Actually, can I mention something maybe here? So, I mean, it's related to ghosts, right? So maybe it's more towards John Donog's talk of yesterday. But anyway, maybe it's more general. So at least in the more conservative approach that that John is following is, we have anyway a ghost, but what happens is that if we take one loop correction, we make this ghost stable. Okay, of course, I will not say that I fully agree, but let's assume that this is really the case, that it holds also for higher loops in the self-energy and so on. Then, of course, what the difference between normal unstable particle and the ghost particle is that here we have some kind of, we have a width which is negative, right? So in principle, in experiments, when we measure width, okay, we usually measure absolute values. We never measure the sign of the width, okay? So I think that also, maybe not in a laboratory like LHC2, because I mean, we cannot test quantum gravity there, but I don't know if in a cosmological collider, we can really find a way to test the sign of the width of a particle, for instance. Because in this case, because of the ghost, we would expect that the width has a different sign, okay? And this could be kind of like a way to really rule out, I mean, alternatives or different approaches. At least I would think just about the Knox case. Of course, it's still quantum gravity, it's difficult to test quantum gravity, but I think it would be nice to just find some smogging signature for each approach, okay? And for each approach, say, okay, this is the smogging signature. If we find yes, then it's something. If we find no, we can rule out the approach, okay? At least, do we have some smoking gun signature which distinguish one approach from the other? Because so far I didn't see any like really distinguishing prediction that, for instance, is in one approach but is not in another, okay? So yeah, it's more maybe this question more towards Donog's approach, but it can be also more general, I think. So
if I may say, how do I know whether gravity is classical or quantum?
Yeah, sure. That's also a question. Yes,
experiment yet.
Of course, that's also a good question.
That's absolutely true. But I mean, to differentiate approaches is important. Well, testing quantum nature of gravity is different thing, but testing approaches to quantum gravity is a different thing.
I would say there are two questions. One thing is to test intrinsic nature of gravity, which is either quantum or classical, but this does not even depend on the approach, because, for instance, as Anupam's also shown a few years ago, so we can test quantum nature of gravity also at low energy. So the quantum nature of gravity itself should not depend on the approach, okay? Because we can test it at low energy, even in a laboratory with quantum interference experiments and entanglement experiments, okay? That can be done. And all the approaches should predict the same low energy quantum nature if there is really quantum gravity. But another question is to test approaches, okay? Here we are, of course, speaking about high energy physics. We are assuming that gravity is quantum, and we are trying to make sense of the energy behavior, okay? But do we really have some smoking gun signature? At the moment, at least in the presence of a ghost, I only see like, okay, if you have a ghost, we have some negative width. Can we measure some negative width or not? Okay, most likely not, because we only measure absolute values usually. Okay, so yeah, I don't know if how to, yeah, I don't know even how to ask the question. I mean, do we have like for each approach, for instance, yesterday, Jones, Phillips,
yeah, like in that sense, that Fakian prescription has some prediction, like you can.
No, Ben's here. Yeah, unfortunately, he's not here.
Yeah, so that has some prediction, but other approaches, I don't know if there is something can be derived and something can be said. I think at least some
questions,
in the context of cosmology. Yeah. So yeah. Sorry.
I see several raised hands. So if there's anybody who has a direct answer to Luca's question, please answer now. Otherwise, I go in chronological order.
Hi, Luca. I just put some couple of papers in the chat. So when you have a higher derivative theory, there are some predictions in, for example, in LHC, there can be some causality violation in particle decays. So if you have some ghost in your theory, there can be some long-lived particle searches, and some of these ghost particles, if they produce, can go the other way or have some micro causality violation. So there have been some prospective discussions on this. I don't know how much robust this is or how much LHC will be able to do, or how much the results are, but I know there are very dedicated plans in LHC for having long-lived particle searches like Matsulla detectors, phasor detector, which will look for really long-lived particle searches. And maybe we can put some bounds if we see, I mean, if it's not the exact signature, we can surely put some bounds on the scale of when these particles can have this kind of non-Gaussian long-lived particle decays. So I just put a couple of papers on the chat.
Alessia?
Yes, so of course I don't have a complete answer to your question, Luca, because of course it is very difficult to identify one observable that would be well detectable and different for all approaches to quantum gravity. First point. Second point, in principle, some of the approaches to quantum gravity could be just different mathematically, but equivalent in terms of observation. So it is not obvious that you could distinguish between them. This is something that we don't know a priori. An intermediate question that you can try to think about is whether one could find signatures of symmetries of the symmetries of quantum gravity. Different theories of quantum gravity have different symmetries. There are approaches that at high energies, for instance, violate Lorentz invariance, and depending on at which scale you do that and what is the precise dynamics and the coupling with matter, you could put bounds on the violation and could maybe I don't want to say rule out some theories, but constrain them quite a lot. In the case of asymptotic safety and probably also quantum gravity, I mean, the basic symmetry is diffeomorphism invariance, or at least asymptotic safety needs most conservative version, because the idea is just to keep as much as we can of the symmetries that we know and the frameworks that we know. And in string theory, you would have more degrees of freedom, but also more symmetries on cosmological backgrounds. For instance, T-duality plays a role, and that would even, at least it could say something about the existence of the de Sitter solution, and in particular, if, for instance, no de Sitter solutions arise in the context of string theory, one would have alternative possibilities like quintessence, and then one could try to put some bounds in that direction. So I think a first think about these symmetries of quantum gravity.
Astrid?
I think Alessia has made a number of excellent points, in particular about that it's not clear that the approaches are necessarily physically distinct. But I would like to sort of, bring up the point that maybe we shouldn't focus too much on smoking gun signatures, but we should focus more on the question of observational consistency tests. So if we do know quite a bit about our world already, and everything that a quantum gravity theory would predict would have to be consistent with that. And I mean, it's probably not surprising if I say again that here matter could really be a key point, right? And in fact, we don't actually know for any given quantum gravity approach yet whether it is compatible with the standard model. So for string theory, it's not settled whether the standard model is in the swampland. For asymptotic safety, there are, I would say, quite promising hints, but we don't know for sure. For other approaches, we don't know either. So there's this whole wealth of observational data on the number of fields, on the type of fields. For instance, the question of whether chiral fermions can be accommodated in a quantum gravity approach, in particular if it has discreteness, is really a sort of key open question. And so I would advocate that instead of looking for novel smoking gun signatures, we should focus on putting the data that we already have to use and figuring out whether there is any quantum gravity model that is compatible with that.
Anish, and perhaps this is the last question.
I think Richard want to say something. No, yeah, I'm sorry.
Sure. Please go ahead.
No, I had seen before the raise hand by Richard, but now he's lower, I think.
Please go ahead.
Richard, you wanted to ask a question before? Or?
Well, I just had a comment, but I think it was already made by other people, so I thought making it.
So Anish, please.
So I have another small question again for Astrid and from BSM model building point of view. So we know that in the standard model, the neutrinos have mass. I mean, for sure the neutrinos have mass, for sure we have that. And if you want to give the neutrinos mass, the mass right-handed neutrino is one of the very viable options. And then if I think of the right-handed neutrino, it itself doesn't have electromagnetic charges, weak interaction, or QCD interactions. So I can think the main interaction the right-handed neutrino has is with gravity itself. So from the perspective of asymptotic safety approach to gravity and your talk matters. So do you have any predictions on this right-handed neutrino mass scale? Because the right-hand neutrino exactly interacts only with gravity and nothing else, and that can be something interesting to look forward to in the BSM model building community. Just a curiosity.
Yeah, just a very quick reaction that understanding neutrino mass generation and Yukawa couplings for the neutrinos is something that is under investigation, but no answers yet.
No, but do you always need a Yukawa coupling? Because for example, if I think in just a scale like the C scale, and if I think it in terms of generating the seesaw scale, just like I mean, for example, generate the Higgs, I mean the Planck scale or the Higgs mass scale. So can you not expect some threshold corrections to come in the UV and change the predictions of the beta functions in the UV that you might otherwise believe in Gaussian fixed points getting changed due to this presence of this heavy neutrino?
Yeah, so in seesaw models where you have a high seesaw scale that is somewhere in the vicinity of the gut scale, you could expect that could have an interesting interplay with quantum gravity. But of course, the simplest way to generate neutrino mass is just to include right-handed neutrinos and a standard Yukawa coupling, which then just has to be very small. I would say that's the most conservative way to get neutrino masses. But of course, there's a whole class of different models that, again, one can explore and understand which of those are compatible or not with a given UV paradigm. And that, of course, applies not just to asymptotic safety, but also to other quantum gravity approaches.
Yeah. So my curiosity was that if the threshold correction matters in your playing of the beta functions. So if I have some threshold corrections coming from the neutrino sector in somewhere in the UV, if that changes your prediction for the quantum gravity sector. I mean, otherwise, as you are saying, it is correct. I do not need to go beyond the standard. But in that case, I have a very, I have to believe in some fine tuning where the Yukawa coupling needs to be very small, and the neutrino mass is very kind of boring. But if I have some,
the electron mass is already quite fine-tuned compared to the top mass. So I mean, it's sort of your personal threshold for fine-tuning that you have to decide on there. But yes, I mean, a short answer, if you put in new physics with certain thresholds, then that of course changes the mapping from sort of an asymptotic safe UV regime to the infrared. So yes, there is sensitivity to that.
Also, if I just may comment, from type 1 from vanilla leptogenesis, you have a bound on the right-hand neutrino mass. So if you want to satisfy the baryon asymmetry observed from type 1 leptogenesis, vanilla leptogenesis, you kind of need the right-hand neutrino mass scale to be around 10 to the power 10 GeV, 10 to the power 12 GeV. Otherwise, you produce, I mean, you produce the asymmetry, then they get washed out. So, so just like have you studied this kind of? So if you have this threshold scale to be 10 to the power 10 GeV, then you satisfy the vanilla leptogenesis, and then you may have some prediction from asymptotic safety gravity point of view.
Yeah, so this has not been explored yet, but it's definitely an interesting question.
Thank you.
I see that Gia is back with a question, and I would suggest that this is a closing question of this session. Please, Gia.
No, I just said actually the answer about this right-handed neutrino mass. So this we've investigated this question about whether gravity, in which sense gravity could generate neutrino masses with some of my ex-students, Lena Funke and Sarah Folkers and others.
Mm-hmm.
And so there, the one source that gravity could provide, one very interesting source that gravity could provide neutrino masses is through the topological susceptibility of gravity. Now in QCD, we have topological susceptibility in pure blue or in QCD with massive quarks. And that topological susceptibility actually leads to the condensation of quark, to the generation of quark condensate and breaking of chiral symmetry through the chiral anomaly. And it looks like that gravity would look exactly in the same way if topological susceptibility in pure gravity would be non-zero. And now in gravity, there are no obvious instantons that would saturate it. But so I had this idea that micro black hole tower, very similarly to glue ball tower in QCD, so saturates the correlator. It looks like micro black holes, they act very similar to glue balls. And so if that's the case, then you can prove that fermions condense and the lightest ones condense. And so the idea was that neutrinos are the ones that condense and they generate their own mass through this condensation. So that is that would be a very interesting source for neutrino mass. And with very different phenomenology, by the way. It's not seesaw, it's a different mechanism. And it would be masses that are very soft and so on. Anyway, so this is the, so you can, these are published, these papers. So.
Hi, if I may have a
No, I'm sorry. This is now closing, really. We just have 15 minutes to the start of the next session, and a chairperson of the next session has already been testing his